Yes, good day, everyone. This is Tom Hengl, Director of OpenGeoHub Foundation. We are running a little webinar, 1 hour, to celebrate the World Soil Day, which is on the 5th of December every year. We invited a couple of speakers to join us on this special occasion. And I will just start with some introduction. So I will just start with some introduction just to introduce a bit the topic and to introduce the stage. And then we are going to have two presenters with us, Uta Heiden from the German Space Agency, DLR, and then Giulio Genova, our soil data expert at OpenGeoHub. And they have two interesting presentations, mainly about the pan-European data sets. One data set Uta is going to talk about is called SoilSuite, and which is mainly based on Sentinel-2 and goes up to 20 meter, I think. And then Giulio will talk about Soil Data Cube, which spans a bit wider time frame, so from 2000 to 2024, but it's at course resolution 30 meter. And we will keep 10 minutes for questions on the end. So if you have questions, you can already use the chatting tool to ask questions. Otherwise, you can keep the questions for the end of the presentations. In Europe, we have soils. Soils are one of the foundations of European civilization. But soils are also increasingly, especially from the Industrial Revolution, soils are under threat. And I look a bit about what are the main trends. I did a bit of literature research, and these are some of the biggest groups of threats. So from nutrient imbalance to water erosion, compaction, sealing, and you can see also here which are the drivers of that degradation of soil, and you can see how many in a percentage of area how many soils are affected by that. This is all just estimated. Nevertheless, it's important to say the number one driver, most likely, it's the very intensive agriculture in Europe. So we have most of European farm fields are still plowed with the heavy machinery, and that leads to degradation of soil. Then we have also from deep tillage, deep plowing, and we have increasingly urbanization. Europe is a heavily populated continent, apart from some regions, and land is scarce. And every year we convert more and more land from some natural use to urban use. Then when you look in Europe across different geographies, you can notice that every region has a different type of problem. So the Mediterranean region, usually it's the salinization, detrification. In Central Western Europe is the nutrient pollution, sealing, compaction. And then in Eastern Europe is contamination from legacy heavy industry and then erosion. So it really depends also on the geography. There is a very nice report on the state of soils in Europe. I highly advise to take a look at it, which also discusses and reviews all the European project outputs and outputs from the work of JRC, Joint Research Center of European Commission. And you can see it's all very systematically listed. There is also a new soil monitoring law. It's aiming at really getting all of the European soils healthy to some degree. It's kind of organized in soil districts, so every soil district will be monitored, and there will be standard descriptors or indicators of soil health. And so that's also exciting that it's been actually now it's official. It's soil monitoring law, although it's not considered something really as a brute force. So it's more like to support member states and farmers to further implement maybe a bit more strictly. So how do we monitor soil degradation? Well, today there's a thanks to mainly to the European Space Agency, Copernicus Sentinel program, then the NASA's Landsat program. Lots of data is now available openly, and here we process the whole of Europe. We process the Sentinel-2 at 10-meter resolution, and we produce the mosaic, cloud-free mosaic. So when you zoom in, you can see in detail different features. And this data, Sentinel available from 2016 usually, and Landsat is available even from 1985, but let's say from 1997. Landsat 5, Landsat 7, higher quality data. And then from this open Earth observation, you can derive number of indices. So there are vegetation indices, there are bare soil fraction or bare soil index. There's also something like tillage index and difference water index. So there's a lot of indices you can derive. And this index you can even derive on a bi-monthly or monthly basis, and then you can really track everything that happens also to land, to soil. And that's what we did in this article. We produced something about, I think, 10 terabytes of data, bi-monthly, different indices, and we made them available as open data, so for everyone. And our colleagues from German Space Agency also produced bare surface spectra. And what you see here, it's actually attempt to make an image of the true color of the soil. So this color that you see, it's one of the first true colors of the soil, but our colleague Utash is going to talk about that. Then these products like a SoilSuite, they're also used to predict soil organic carbon. So this one is output of colleagues from the World Soils Project. So they produced pan-European 20-meter resolution soil carbon predictions. And we also produced at OpenGeoHub, together with the colleagues from FSO Health, made organic carbon density predictions with also multiple depths, and that's also been made available. We also then produced the whole world, also 30-meter resolution. Currently, publication is in review, but you can visit world.soils.app, and you can access this data and download it. Also, the soil spectroscopy is taking off. The instruments are smaller and smaller. They are also easier to afford, and these instruments can be used to on the ground in situ measure soil properties using soil spectroscopy. This instrument here shown is actually made in Germany, and it costs, I think, about 1,000 euros or something, and allows you to determine about 15 soil properties within days. Hyperspectral technology is coming. There's already publications with Prisma and Nmap hyperspectral sensors. This one, Nmap here, has 246 bands. So this is way beyond what Sentinel has. And so that's also used directly. There's also CHIME, Copernicus hyperspectral mission coming up. So that's exciting. That will be in few years. Also generating open data. Then there's AI technologies being integrated with this Earth observation data cubes. This is an example of WRI Global Nature Watch platform, where I think this data cube is combined with Gemini AI. It's combined to allow people to seamlessly select some area and get some statistics and ask questions using natural language, so they don't have to know how to code and doing some complex spatial analysis. So what can you do to help reduce or reverse soil degradation? So you see there is intensive soil degradation in Europe still. We're talking large percentages of European soil are either polluted or degraded or under loss of biodiversity. So what you can do, very simple, if you're a farmer, you can consider the regenerative agriculture practices. You could try to keep the soil covered for most of the year if possible, switch to agroforestry systems, and also you should start tracking your field using open Earth observation data. We make this data openly available, and idea of this webinar is to popularize that, to really show you that this data it's available to you at no cost, so you can use, especially in Europe, you can use this pan-European data without any need to invest. And we had a large conference in April here in Wageningen, and we published this report. And for those of you who are more interested in these developments of Earth observation, soil spectroscopy AI technology, most likely you can, most welcome, you can watch the videos from the conference. They are all also publicly available. Whole conference been video recorded. You can watch the videos. They're also listed on our project website, AI for Soil Health. So you can find there all these materials, and also within our project OpenNet Monitor Cyber Infrastructure, you can also find link to the original Landsat archive, which is about 150 terabyte of data, bi-monthly analysis-ready data. And now I would like to switch to a first guest speaker, Uta Heiden from the German Space Agency. So Uta, without any further ado, I pass on the slides to you, screen sharing to you.
Yeah, thank you very much, Tom. Can you see my slides? Can you hear me well?
Yes.
Okay. So hello, everyone. I would like to speak about the SoilSuite, DLR SoilSuite that we developed. I developed my team, Pablo, Paul, Peter, and some of the products also in cooperation with other partners. In this case, it was ISRIC. So I will shortly introduce you to what does it mean, the SoilSuite. I will say a little bit about the soil composite mapping processor. So that's the processor that's producing the SoilSuite. I choose a little bit some aspects of the ACMAP methodology. I show you some examples if I still have time, and a short summary. So just to give you an idea what is actually the SoilSuite. The SoilSuite are 9 image data products across Europe in 20 meter spatial resolution that are informing about the spectral information and statistic properties of European soils. And these products are mainly used, or our primary purpose is actually to derive soil properties. You can access this data. I put here in the QR code. It's via our DLR GeoService webpage. We have a map service. You can download the data for free. You can integrate it in your API with stack metadata and so on. So we have a description of the methods and the data products there, a DOI for referencing. So feel free to look at the data, to explore the data, to use it for your processes and to test the data sets. The same we also have developed for Africa, for 3 African countries, Rwanda, Kenya, and Ethiopia. It's the same thing, also freely available. You can access it via this QR code, map service, download stack metadata. So we are happy to get any feedback from you about these data sets. So I would like to start when I come to the processor about the main challenges of observing soils with optical Earth observation. And here we have a Google Earth image, Google Earth Engine image, and it shows, well, the bare soils are quite rare and often covered by obscured, and it's mainly clouds, also thin clouds or haze, cloud shadows. These are the usual problems. In the case of soils, we also have vegetation, which is the green vegetation, but also dry vegetation, which is actually good in terms of soil health. But for looking to those bare soils, the bare soil spectra that we wanted to achieve, it's an issue. So a couple of years ago, the community came up with a method of temporal compositing. So how is it working? You have a time stack of data, and on a per pixel basis, you apply any temporal averaging. And then you get a reflectance composite. It's kind of a cloudless image that you might be known from Google Earth or Google Earth Engine or so. So in order to get the bare soils, we can try to find out which the pure bare surfaces are, and we are doing that with the spectral index and the threshold. And when we can do the same, we can select these bare soil pixels and do a temporal averaging, and then we get the bare surface reflectance composites. In this case, the average was based on mean. You can also do it via median, but this is also something specific, I think, on the SoilSuite. We were doing the mean in order to get also to the standard deviation, so the spectral variability of the soils. And of course, you also can derive statistical information, like how often do you see the soil in a bare condition. So this principle we translated into a processor, the soil composite mapping processor. It's a fully automated and operational processor. Then it's tested and validated very much on Europe, but we also have applied that for Brazil, West Africa, Canada, and parts of China. So it can be deployed on different cloud platforms like DLR's high performance data analysis platform Terabyte. And we also have deployed it at the Open Telecom Cloud. What I also wanted to say is this processor is not very fixed, so you can, according to the needs of your project or your idea or your product you would like to get, you can configure this processor. So you can select between if you would like to use Lancet or Sentinel. In case of Lancet, you go more into the history. You also can define the temporal settings. So sometimes it makes really sense to observe long time series, like 5 years or 8 years. Sometimes you just want to have the bare soil frequency, for instance, on a monthly or on a yearly basis. So this is the things you can really define. And then we also implemented a couple of filters, like here the minimum sun elevation for a better spectral reliability. This soil-specific cloud screening, I decided not to speak about that, but if you question, please feel free. Here on the right lower side, you can see that this could very much increase the quality of the surface reflectance, bare surface reflectance. And then we have also the possibility to implement different spectral indices for deciding what's a bare soil and what not. But I will come back later to that. So currently, we also working on publishing the processor itself on Apex. It's an ESA platform, so it's an OpenGeoHub user-defined process. It's actually the source code in Python available. These algorithms with this platform can be integrated in other OpenGeoHub processes or can also be run standalone. The satellite data you can get, that's actually the beauty you can get via the Copernicus data. Oh, okay, it's a CDSE, so it's a Copernicus platform that contains all these different data sets, like for instance, the Sentinel data. And you can execute this via webface or OpenGeoHub client. Now, I would like to draw your attention to two actually specific things, methodological things of the CMAP. So the first is how we derive the thresholds, because this is also an automated process. And then I will also speak about the evaluation of the some of the products. The thresholds are very important because they define do we have a bare soil pixel here or not. And so we had to come up with a technology that is very generic, it's globally applicable, but at the same time, it also shall allow for regionalization. So maybe thresholds differ per region, per environmental conditions. Then what is also quite important, especially for multispectral data, is that we wanted to account for the spectral similarity that we have between the bare soils and the dry vegetation, so the non-photosynthetic vegetation. It shall be spectral index independent. We wanted to be not fixed in that, and of course, fully automated. And so we came up with this idea. Actually, we are calculating, we are choosing an index, let's say a vegetation index, and calculating for a time period the minimum composite. So we just take the minimum, the minimal index values and put that into a composite. And that way, in the crops shall show up as bare soils because minimum vegetation, and the grasslands show actually then the dry vegetation. And now we have these two competing land cover types that we would like to separate as much as possible, although they are spectrally similar. So for this case, we need a land cover classification in order to get an histogram, a normalized histogram of the spectral index values. And by looking to the histogram, you can see in the blue that are the croplands, which have likely bare soils, and in orange the grasslands, which is likely dry vegetation. And you see the different peaks, but you also see the overlap. And with our HiSec technology, we are in different iterations, we are looking for the best threshold that separates or minimizes these spectral overlaps. So this is done with our HiSet technology, and we are coming up with thresholds. Okay, before I want also to speak about the land cover, because this is important to get to these histograms here, and they should be as clean as possible. So we were looking for a land cover data set that is globally available, and we came across the ESA World Cover, which is a very nice 10-meter land cover data set. Is working quite well. However, you can see at some of the field borders some mixed pixels, and these pixels screw actually our statistics. So we came up with an approach to measure the kind of temporal variability index. And you can see here on the borders, we have lower values, which means that here we do not have so much changes from bare to vegetated. And that means that it might be more mixed in at edges, at paths, and so on. And we want to get rid of these pixels to not screw our statistics of the histograms. And at the same time, we also found some grassland areas here. So therefore, we could improve the land cover, and then we derived the thresholds per UTM tiles. You can choose also any other spatial unit, which makes maybe more sense. For simplicity, we just chosen these UTM tiles here. But you start to see differences here in the Ukraine. You have much lower spectral index thresholds to select these bare soils than here on the British Islands or here in Scandinavia. However, you also see that we have some edges between these tiles, and this is something, or especially here, this is actually what you don't want to have, because that is then visible in your resulting compositing products. So we applied a lot of interpolation, so proximity interpolation, histogram aggregation, and also we have made an aggregation based on biogeographic zones. And this was the result then. And you still see that there are regional differences, but in much smoother way. And if you have a look to the result, a comparison here, you see where we applied the threshold without interpolation, and you start here to see here on this product, it's bare soil frequency, so it gives you how often you can see the bare surface, and you can see that you have these edges here in, and if you apply the interpolation, it's getting much smoother and without changing completely the values. So this was one of the methods. The other was we were thinking a lot about how we can actually validate or evaluate our bare surface reflectance composites. And that's not so easy because I'm not aware of any validation data set for a bare surface reflectance spectrum. So, or for a composite spectrum. So, I mean, then this, at the same time, we also were looking for data that is available for whole Europe, and not just for small test areas, where you go out with a spectrometer and are taking spectra each week, for instance. And at the same time, we also thought about what we actually wanted to know. I mean, we wanted to know, is the selection of our index, is that useful? Is our index the best, or are there different indices that are working better in a European context? Thresholds, are the thresholds correct? Or is it actually useful to have these different thresholds across Europe? Or is it better to have one global? It has no effect on the quality? So first question was, what is our reference? And we decided for the Lucas, or thought we know that the Lucas spectra are a totally different measurement. It's based on lab measurements, it's sieved, it's dried. However, we decided for it because first it is available for Europe, but second also it's the main database for European-wide soil property mappings. So this is the main data set that has been used. So in that case, we wanted to come as close as possible to this Lucas spectrum. And how have we done it? So first, we try to answer the question, which spectral index is actually the most suitable one? And here we collected a couple of indices from the literature. And we, for each of the indices, we calculated the ideal threshold for each Lucas point. So which is the threshold that is not able to be, so with this threshold we cannot be better, or we cannot come closer to the Lucas spectrum with this composite spectrum. So that was the first, and we used this by minimizing the angular distance between the composite spectrum and the Lucas. And with this, we came up with a performance measure here. The lower, the better. And as you can see here, NDVI is not performing very well. And if you combine that with two other indices, you can get very, very well. Our final choice was not the best one, but the combined index, because here we just need one threshold data set instead of 3 threshold data sets. So thresholds are never something you would like to have. You always have to decide. It's always a binary decision. So you really would like to avoid as much as you can thresholds. So therefore we choose this combined index. It's actually a combination of the NDVI and the NVR. So based on this threshold, we also tested, is it actually useful to do this regionalized threshold data sets? So, and we try to come up with a kind of performance test where we measured on the one hand the distance from the composite spectrum to the Lucas spectrum, which is shown here, and actually also the coverage. So how many pixels do we get with certain thresholds? And you can see here, this is our regional threshold data set, where we have a quite high mean angular distance, so low mean angular distance. That means we have a high quality. And at the same time, we also have quite high coverage of soil composite spectra. And then we made the test with a couple of different thresholds that are globally applicable for whole Europe. And you can see none of them is reaching whether this high the low mean angular distance nor the high coverage. So it always comes with a price here. And that was the decision where we then were keeping these regionalized thresholds. And with this technique, you can not just check if your index is correct, you can also check for small changes of your algorithm, maybe an improvement of the clouds or any other improvements you are doing in your processor. And that's actually a very, very central tool for us to improve our methodology. Okay, I still have some minutes, Paul, Tom, is that okay?
Yes, but if you could finish in 2-3 minutes, that would be.
Okay. Yeah, I will do that. So just a quick intro the SoilSuite products. This is a simple, actually a byproduct. It gives you in the brownish colors the areas for which you can see actually their surfaces. For all the green ones, it's just permanent vegetation. For others, it's water bodies or urban areas. And we use that for a service, an operational service of federal ministries in Germany. They use that for finding out areas which have not plowed within 5 years, because that is then declared as grassland. So this is going into operational service. The main product is the bare surface reflected composite, and it has been used in many projects, CAP for soil, MRB for soil, world soils, to derive soil property maps. And here is an example of the Harz region. The brownish colors are the bare surface reflectance spectra. And this is the derived soil carbon map by our partner ISREC. And it comes also with uncertainty, which is, I think, very important for these products. And this was actually very interesting because here we had a cooperation with the Federal Ministry of Mining, Geology and Raw Materials. They said, okay, we have our own data. We are not dependent so much on Lucas. We have our own soil core data, and we would like to derive soil carbon stock map for the whole federal state. And they were quite amazed about the quality. So that example just shows you that you not just rely on the resulting products or property products, but you can also use the SoilSuite for your own modeling of your soil properties. We are also very proud to be able to get the standard deviation, so the spectral variability of the soils, and I show you very quickly how this looks like. This is the bare surface composite, the mean, so where we just average it with the mean. And this is the standard deviation, and you start to see differences in the spectral information. And if you look to the spectra, it's really very distinguishable, and it has soil properties that are, so the differences are based on soil properties that you can then also use for your modeling. So it's an important additional data product or covariate that you could use. And this is lastly, the bare surface frequency, very important for soil erosion measurements, for instance. But in this case here, we cooperated with a company, and they used these data sets to distinguish the conventional farming practices from the regenerative farming practices. So that was also quite successful. That's from my side. So a CMIP is an operational processor to get data for spectrostatistical information about soils. Our data product we call SoilSuite. It's available for free for Europe and for some African countries. The processing parameters and methodology are evaluated. The image data products are tested for soil property mapping, monitoring, and so on. And the source code is available in Python, OpenGeoHub, at Apex at ESA. Thank you very much. That's all from my side, and I'm happy afterwards to receive your questions.
Thank you, Uta. There will be questions, I guarantee you. But let's move on to Giulio. The second talk. Same geography, similar objectives, but also different types of outputs. You can share a screen, Giulio. Yes, we can see your slides.
Okay, great. So thanks everyone. Happy World Soil Day. My name is Giulio Genova. I'm a postdoc soil data expert at OpenGeoHub. And today we are going to talk about the soil health Eco Data Cube. But first, we would like to acknowledge that there is a lot going on at the European level for soil. We are just back from Brussels for a meeting for the EU soil mission. These are the projects that are currently in the mission. 63 soon will be 80, and yes, we would like to acknowledge that some of them do mapping, and this was also mentioned by Tom and Uta, so I will go briefly. But there are some projects, for instance, dealing with MRV, measurement, reporting and verification of organic carbon, MRV and MRV for SOC, and yeah, sometimes they will have mapping components. The SoilSuite that was just presented was also used for the World Soils project, Cup for Soil, and these are some outputs from that project, and also Holy Soils. So it's important to notice that there is a lot of efforts into mapping soil at the European level. And with the Eye for Soil Health, we are also dealing with that, focusing on, of course, soil health and especially trying to estimate trends. So the soil health Eco Data Cube, soil health data cube is the main purpose is to be a platform where more detailed computing to estimate trends for soil health can be achieved. The main components that we highlight here are the manual, SHDC AI for soil health.eu. You see the link where we explain how to access the data and explain a bit more about the project and the data sets. The web platform, which we call ecodatacube.eu, where you can visualize the data. And the catalog, stack.ecodatacube.eu, where you have the possibility to access, to see, search, and access the data sets. But how do we achieve this? So we map soil at 30-meter resolution, and we use what I would say it's a usual digital soil mapping framework, which looks like this. It's quite intimidating. But what we do is gather spatially explicit so-called covariates. Those are the independent variables of our model. We gather soil observations, and then we mash them together in a regression matrix. Now, what we do, it's important to know that we do spatial and temporal modeling. So we also, the overlay we do, so the matching between the soil properties and the maps we have is done also temporally. So we match the closest observation for the soil, also for the different satellite imagery and the rest of the covariates. Then we have our own software that we developed. There will be slides afterwards. We build a machine learning model, and then we can predict at scale, in this case, 30-meter resolution for Europe. And of course, this data is then checked and assessed for quality, and also sent to the front end, which means that people can visualize, and also it's stored somewhere so that people can access it. This is a more like simplified version of the framework that we use, and it shows you what kind of technology we're using currently. So we use Python with the scikit-map library. That is the modeling part. And we actually use C++ also because we compile our models to make things faster. You can imagine that this, computationally speaking, this is hard to do. We have 20 years time span, and also 30-meter resolution pan-European. And then therefore we use a workload manager with our high throughput computing infrastructure at OpenGeoHub to run everything. And even simplifying even more, basically we have our Earth observation data cube. That's our covariates, our independent variables. We have our point soil data. We create a regression matrix, space-time, and then we build our machine learning model. So what do we produce in terms of soil? This is the list of soil properties that we currently have. It's texture, so sand, silt, and clay. That's organic carbon, so organic carbon density, pH in water, pH in calcium chloride, bulk density, and extractable potassium, together with the WRB soil types. We just updated, and by just I mean just like a few minutes ago, we just released a new version of the front end. So you will see the new maps available, and so that's very fresh. What is new is that we added some soil datasets, namely lime soda and HSDOS. It's approximately 6,000 points more. We added two important new covariates, the peatland map for Europe, and also the glaciers forms that we acquired from project partners in the For Soil Health project. We fixed a problem with texture that was changing too much in time in the area of Romania and Bulgaria. Added the last timestamp. So we have bi-yearly data, and 2022, 2024 is out now, and you can access it. And we added the cadastral parcels from 10 countries. So at the European level, there is within the Inspire framework, let's say, countries are sharing their official cadastral parcels, and we are downloading them, putting them on our infrastructure, and also sharing them, so you can visualize your own field boundaries if you're lucky that you are in one of those 10 countries. But more countries will come, and we'll have them, all of them soon. So that official boundaries for farm fields are available on the platform, and you can have a look. And also we are adding an uncertainty visualization for some layers. This is still experimental, but it's there. This is, I'm not going to go into the details of this, but before, compared to the previous version, we have a slight improvement in accuracy for most properties. But I would like to say that spatial patterns especially improved, especially for clay and texture in general. So what does it look like? This is actually the previous version, but because we just updated the data cube, but it doesn't change much. The difference is that you will see that you get up to 2024 down here. So you have 24-year time span, 4 depths from 0 to 200 centimeters. And you're able to select and search for the soil properties. We also have other variables like climate, land use, the field boundaries, as I said, and many more. And this is so the platform that you can go to is egodatacube.eu. This is how it looks like in more detail. So this is a zoom in the Netherlands, if I'm not mistaken, of soil organic carbon density map. And if you click on a point, you see the temporal trend. You can choose between a bar visualization or a line visualization. And right now you will also have uncertainty in this kind of visualization. But so how do you access the data? How can you actually use the data for your own purposes? So it's very easy. You go to stack.egodatacube.eu, and then you can copy the link and add it to your QGIS or even whatever other GIS supports HTTP requests, and directly visualize it in your GIS and do operations with that. So this is the way to do it. You basically get the link. The link looks like this at the bottom. You get it from the stack catalog. You choose one variable. In this case, is pH. You copy the link here, and then you go to your QGIS. In this case, add raster layer with HTTP, and then you will visualize the data and can also work with it. We have a naming convention, so you see these very long links, but they mean something, and it's useful to have information directly in the link. It's the variable name, the method used to assess, to measure the variable, the statistic, in this case mean, but it can also be the quantiles if you want to use the uncertainty layers to understand how uncertain the measurements are. Well, the estimates are, sorry. Then you have the depth, the time frame, and also the region. In this case, it's EU, then the coordinate reference system, and also the version. In this case, we're using versions as dates, but it might change in the future. It might be just 1.1 or something like that. Not only that, but we also are sharing a subset of the soil training points that we used. Those are the ones that we were able to share because the license allowed us to do so. And the standardized table is available. You go to ace-htc.ai for soil health.eu, which is the manual, and you will see in the download data tab the link to get the CSV file. So it's a table. So I hope you enjoyed and you will enjoy the data and also provide feedback. I want to also highlight that we are continuously improving and integrating new data, trying to improve the accuracy and getting feedback from people. So how could you contribute to this? Of course, you can give us feedback. You can donate point data. That's very important for us. We rely on the Lucas soil survey from the European Commission, but also many other data sets from different countries. We can discuss about the license, it's no problem. Or, I mean, of course, we encourage to have open data, but it's also okay if the licenses are slightly more restrictive, and we can discuss about it. So donating that is very important because this will improve the models. You can join our workshops. We have a summer school every year, but also coming up the Soil Health Now conference. Follow us for the updates on our social media for this. Yeah, and then of course, if you produce any data sets that are pan-European, of course they have to be within the scope of the project. Please share with them with us. We can host them and reshare them. Yeah. So with this, thank you very much. I think we can be open for questions now.
Thank you, Giulio. That's great. And I shared, Uta and me, we shared some of the URLs to access the SoilSuite and to access the Ecodata Cube. And we are open now for questions. You can ask questions best using the Q&A. So you just type in the question there, and then you just have to say if it's for Giulio or for Uta.
I'm sorry, I lost you for a couple of seconds. So if there was a question to me, you have to repeat it. I'm sorry.
Sure.
I'm very sorry.
Yes. Well, I can kickstart the questions for you then, Uta, if you can hear me.
Yeah. Okay.
So, like, you have this 5-year interval, these composites, but I assume that you could do more, right? You could do a time series.
Yes.
You could maybe do every 5 years or every 3 years.
Yeah. So in the World Soils product, in the World Soils project, we calculated 3 years time frames and 3 kind of time windows. So to get an idea about the trend of the soil properties. So, but that's definable. So you can do it from, I don't know, from whatever time period you would like to do.
So you could soon have, for example, a time series of like every 3 years.
Yes. Yeah.
Of these indices, and especially what's very interesting is the bare surface fraction, and this standard deviation that you show. That's super interesting to see, like whether that changes through time, and where it changes, and where is a positive, where a negative change. So when do you think that could be made available by DLR?
What do you mean? That's 3 years periods?
3 year, or I don't know, or like you do now 5 year, but
Yeah. Okay. So
let's say
I mean,
Sentinel will soon be like 10 years, so you could have maybe three periods.
Yeah. Well, so first of all, so as a starting point, we decided for 5 years, because within 5 years you can get more bare soil pixels into your composite, which makes your spectral composites quite stable and robust. But we also got a lot of user requests that say, well, especially the statistical data we would like to have on a yearly basis. Can you hear me actually?
Yes, we hear you
So
fine.
on a yearly basis. So but at the same time, we also wanted to make an improvement. So we are currently working on a bare soil calendar, which gives you per day the information, is that a bare soil or not. And so once we have that developed, we will publish a new data set, a new SoilSuite data set that comes yearly for the statistical products, including these new products for the bare soil dates. And I think this is quite useful and also unique, because you can use it then for any soil erosion monitoring, for instance. For that purpose, you need mostly exactly the date where you can see bare soils.
What I find exciting about in your talk is that you actually have some applications where you have German government using your product to, for example, to distinguish is it a grassland or not. So it's kind of used for spatial planning, or for maybe for subsidies, and so that's very exciting. But can you give an estimate? You're long in this field like me. What do you think? Like, how much are we using like Sentinel-2? If you look at the applications in agriculture, so everything that is possible relatively quickly, how much do you think we are utilizing? How much do we reach the like actual farmers?
I do not think that we reach really actual farmers. I think we are the usage of our products, also your product, by consultancy companies that actually consult farmers. They are increasing. But I also think what these companies need is continuity. And that's what a research institution, of course, cannot really guarantee. It can be guaranteed by companies, and that's the hope for where we are investing a lot, is on the Copernicus service. I hope that really these products, not just the soil properties, but also the input data that we have produced, like the SoilSuite, will be published on Copernicus, so that everyone can then use it, do their own modeling with their own really precise data for their own specific area of interest. So I think this is the more, from a farmer perspective, better way to go, instead of using these large scale continental products. I think this is another user community. It's more like for EEA, for serving to the soil monitoring law. That's so important that these data sets that you are creating and also others creating is being published for free.
And tell us also, like I mentioned this hyperspectral. So there's this Nmap and there's Chime coming up. So tell us, like people ask me, like, is it really going to be like revolution? I mean, are we talking like that the accuracy of like mapping soil carbon or I don't know some nutrients? Do people think that it's really going to be much higher, or we still have to wait to see, from application to application? And
Yeah.
maybe you don't need actually so many bands. I mean, you go from like 10 bands to 250 bands. Maybe maybe there is not a like significant increase. What is
Yeah.
your feeling so far?
Okay, my second heart is beating hyperspectral, so that's my background. So I have to say, of course, you will not use. So first, the question was if this hyperspectral data will really be a game changer, and I think yes. There's one game changer, is the hyperspectral data. It gives us much better information, spectral information. We can then go really to physical features. We can measure in a physical way, not just in regression. But the second that I also experienced very much is what really increases the quality is the calibration data. The more dense data we have, the better will be your modeling accuracy and your accuracy results of your results. So it's nice, it's continued, but it's better to have more dense data. So that really drives also your quality. And according to your second question from hyperspectral, I just forgot.
Well, for like, is it going to make a change for like soil carbon mapping or soil nutrient mapping?
Yeah, you were also asking about if we really need all these bands.
Yes.
And this is my answer is maybe because for each parameter, for soil organic carbons, for instance, you need spectral information across the whole spectrum. So maybe not every band, but maybe every 10th band. For nitrogen, you need a specific absorption feature in a specific region, and there you really need all these bands in this region. For iron oxides, you have in the visible and near infrared a lot of features that you need to be parameterized. So it's difficult to say per se for soils. So just choose these and these bands. The message is for each parameter you need different bands, and that's actually the beauty on hyperspectral data, that you can choose it. You can choose from all the wealth of the spectral information you can have. And I think it's definitely improving it is improving the quality of our retrievals.
Okay, just for the sake of time, we'll have to stop in a minute. Just the last question to Giulio. What is in your career? What is the most exciting thing about, you went to modeling soil data, soil mapping. What is the most exciting? You're a younger person. What excites you the most? What should we all look, especially young people like you?
Yeah, I think that's unexpected, but it's a very good question. I think making impact. So having these data sets being used with confidence, and getting there. I think it's a long journey. But yeah, so what you just asked to Uta about, are the farmers using this data? Are we getting there? I think that's what is exciting, right? So we are working a lot on these on the infrastructure, on the modeling, and improving the models. But eventually, we will have to get to actual people using them in a consistent way and with confidence, and
with this, we're going to stop our webinar. Thank you so much for Giulio and Uta. and we will share the video recording. Just subscribe to our channels, and you can, if you miss something, some important information, it will be shared. Happy World Soil Day, and also happy upcoming Christmas and New Year holidays. Bye everyone.
Ciao.
Thank you. Ciao, ciao.
Bye.